In this video, I'd like to talk about the security of protocols. And the definition that I have here is that a protocol pi is secure if it is impossible for an adversary A to break it. So let's think about this definition a little bit. So first of all, we need to remember what a protocol is. And the basic idea is that there are a couple of people and they're going to talk to one another, and they may be running algorithms on their own to get answers as they are going, and use that to determine what messages they send to one another. And basically, what we're saying is that we're going to have this protocol be still with this honest party who's going to run the algorithms as they're stated, but now we have this adversary who is going to try and send malicious messages or try to figure out something that they shouldn't from that protocol. And so with security, we're saying this is not going to happen. If it's secure if this adversary can't achieve her goal, which is to break the protocol. We'll call the protocol pi, so the adversary can't break pi. Okay, so that gives you the overall idea of what's going on, but the English description that I had here is actually not very rigorous. We kind of need to figure out what breaking a protocol means in context. And it turns out that it depends on the cryptographic protocol. I've been so general here. I just said a protocol, but a protocol for what? These messages here could be anything, right? A, B, and C are not specified. So it depends on what you want to achieve. And that depends on what you're trying to, what kind of protocol you need to use, right? So basically, with a hash function, you would want to achieve something called collision resistance, meaning that if you have two hashes, they should not be equal. With encryption, you want to ensure that nobody can figure out which message it is, at least informally. Now, once we know what that specific cryptographic protocol is, we would replace this protocol pi with, a hash function h, and say it's collision resistant if it is impossible for an adversary to find a collision, for example. And the way that we're going to prove it is going to be with what's called a cryptographic game. When we talk about a cryptographic game, we basically think of that adversary as a computer who also has the ability to, quote unquote, flip coins. In other words, it has access to a random number generator. And so basically what happens is this adversary is going to try to maliciously interact with the protocol, which we were calling pi over here. And they're going to send maybe malicious messages or try to learn something they are not supposed to know. And that's in contrast to an honest interaction here, where all of these messages that are being sent, A, B, and C, are done correctly. These are done according to the protocol. So this cryptographic game, which is played with, you can think of it as a person, basically this challenger. They're going to have this input that describes like the size of the protocol. I'll talk about this more in a second. And they're going to invoke both the honest parties of the protocol and the adversary and look at the interaction. At the end, the adversary is going to output some sort of result which will yield true false. And if the outcome is true, then it means that some bad event happened and the adversary was able to break the protocol. This honest pi over here, this could be like one person who's just interacting, or since we're eventually going to be thinking about this kind of multi-party computation, maybe there's lots of miners on the blockchain, it can also be a whole group of people. And they can all be interacting. So this interaction here can get relatively complicated depending on, again, what exactly that protocol is. I'd like to introduce a vocabulary word. This word, negligible. So earlier, I said that we wanted A to not be able to break the protocol, but this was not very rigorous. So a better way to say this is A cannot break the protocol except with negligible probability. And of course, yet another way to say that is to say the probability of the bad event is negligible. Negligible basically means exponentially close to 0. We are going to write it to be dependent on a parameter kappa. So we would say something like the adversary cannot break the protocol except with 1 over 2 to the kappa probability, or 2 to the negative kappa, which gets really close to 0 as kappa grows larger. Now, depending on what you're reading, you might see different parameters here other than kappa. We might also talk about things in terms of n, O of poly of n versus O of poly of kappa. So please be aware of that just in case that changes. But there is this security parameter that we are interested in. Good. Another vocabulary term I want to give is probabilistic polynomial time, or PPT for short. And what this means is the adversary can run in O of poly of kappa time. So it is polynomial in the security parameter. If you're familiar with big O notation, then you understand the concept of runtime. And then the polynomial can be to any power. So we could have O of kappa squared. O of kappa would be pretty good, but you could go really bad and have O of kappa to the 10,000, things like that. But I can't have runtimes that are exponential. And really the point here is that A, the adversary is not allowed to brute force or try to run basically almost forever to try and break the protocol, because if they were to check everything, then it would be possible to break the protocol in a lot of cases. But we're not going to allow that most of the time. For the probabilistic part, that means that A has access to a random number generator somehow, so it can flip coins as part of its algorithms when it's working with the game to try and break the protocol. So right here, basically this interaction is going to be polynomial in kappa, and the adversary might be picking things at random to send out his malicious messages. Good. Let's just formalize this. I'm going to say something very similar to what we saw on the previous slides. But now we have this more rigorous definition. A protocol is secure if every probabilistic polynomial time adversary succeeds with negligible probability. So the key concepts that I brought up before were the polynomial time algorithm and the fact that it was a negligible function. And just for completeness, for those of you who would like to see it, I'm going to give the precise definition of negligible. A function from f from the natural numbers to the non-negative real numbers is negligible if for every positive polynomial p there is an integer n greater than 0, such that for all kappa greater than n, we have that f of kappa is less than 1 over p of kappa. So this is not strictly necessary to understand what's going on in the class. This part of the definition, the more rigorous definition than what we saw earlier, is something that we should know for this class. Let's just remind ourselves what we know about the adversary. The adversary runs in polynomial of kappa time. Kappa is the security parameter. The adversary knows the parameter kappa, and in fact, due to Kirchhoff's principle, the adversary knows all the algorithms in the protocol, every step. Nothing is secret. So when they're doing this interaction, and there are all these algorithms being run on one side and all these algorithms that the adversary might run, none of this is kept in secret. The only thing that might be secret is if there is a secret key, but that's the only thing. So basically, our protocols are designed to be secured even though the adversary has access to the code of that protocol. Looking again at the challenger game where the adversary is interacting with the honest parties as part of the protocol. One thing that we saw earlier but I didn't explain was this 1 to the kappa. So now we know that kappa is that security parameter, and it has to do with the length of the input. Because the longer the keys are, the more secure a protocol should be. And so what we will often see is that the adversary is given access to that kappa. So we'll write it as A, which represents the adversary. We can see that here and here. That's the same letter. And then this 1 to the kappa indicates the length of the input. And the length of the input is related to the amount of security level that you get. Okay, we'll talk about this a little bit more later to really work out what this exactly means. But understanding that kappa has to do with how long the strings are that the adversary is seeing, and that the length of those strings have to do with the security level, that's enough for now. One thing I mentioned earlier is that so far we've just been talking about generic games. So there is this pi, and there's some sort of interaction, but it's not clear yet what exactly that means. So just as a couple of examples, just to say what these interactions could be, if pi were some sort of encryption scheme, then the interaction would involve the adversary choosing messages and then receiving from the interaction ciphertexts. And then at the end, to win in this true-false part, the adversary would have to output what message was encrypted. Another one that you might think of is a signature scheme. And then here the adversary would just try to forge a signature despite not having knowledge of the secret key. So sometimes these interactions might not actually involve very many steps. It could just be the case that the adversary has access to all the code, can do everything at home by herself, and then only needs to output the result. So that would be an example like if we had, let's say, like a hash function. Since the description of the hash function is given already, the adversary just has to output two values such that there is a collision, right? So again, it depends. These are just a couple of examples to help clarify what kinds of things we could have. So far, we've been drawing this game as a picture with the arrows for interaction and showing the inputs and outputs. But of course, you can write this in something that looks a little bit more like actual code. So let's look at some pseudocode for this game. And so this is basically what a game-based security definition is going to look like. It's always going to be written as a sort of algorithm. This label here, you might write algorithm. You may also write just game to indicate what it is. Okay, so with an algorithm, you need to have an input. And so the input here is kappa. And we also have some parameters, which are the exact protocol that we actually have, and the adversary. Okay, and so remember that challenger, that game is on the outside. It's going to invoke the honest party. The honest party also has poly k time. If there are any more arguments depending on the protocol, that will be added, and then it's going to invoke the adversary with, again, poly k time and whatever arguments are needed. And this part here with this arrow indicates the output of the adversary. So that's some notation. Okay, and now the game is going to evaluate whether the adversary has been successful or not. If they are, that's kind of bad for us, but the game will return true. Otherwise, it will return false. So just to review algorithms in terms of input and output. The input is kappa, and the output is Boolean, true or false. All right. I'm going to end the slideshow here. Just want to review what we just talked about. We talked about probabilistic polynomial time algorithms, negligible functions, how to define security and protocols, what the adversary looked like, and games. Right? So the real point of today is to understand these definitions, and then once we do, we can start actually using them for real protocols and actually applying them. Thanks for watching.